Good afternoon, ladies and gentlemen. Welcome to this session on taking your application to memory. Hope you all enjoyed your lunch and are ready for this last part of the rally. My name is Rasmus Reinholdt. I'm Danish, not that matters much. I have worked with SQL Server for the past many years, personally working as an independent consultant at UNAPS, part of the United Nations, doing data warehouse architecturing. My contact information's at the bottom of this slide, and please feel free to contact me afterwards if you have any questions. So, how many of you normally, day-to-day work as developers? Well, about half. That's good, because this is a talk for you. The rest of you are very welcome to hang along. I will give you an introduction to memory optimized tables. I'll show you what you can do and what you can't do with them. And then I'll show you what Microsoft says that you can't do, and afterward I'll show you how you can do it anyway. Along the road, I'll show you how we went about converting our application to memory optimized tables and natively compile store procedures. So it's a practical talk. Most of it will be showing you tips and tricks, things that we picked up while doing actually coding, the way we did it. I'm not saying it's the only way or the best way, but it's the way that we did, and it worked very well. So it's not a deep dive into memory optimized tables. I'll start out by giving an overview of what memory optimized tables are. But we'll not be looking at stack traces or debugging DLL files and stuff like that. We'll be looking mostly at T-SQL and how to code for memory optimized tables and natively compiled store procedures. So, meet my good friend Hackathon, the code name for memory optimized tables. The memory optimized tables comes as a built-in component to SQL Server 2014. It's available in Developer and Enterprise editions. You cannot activate it, you can't deactivate it on the installation. If you have the right SKU, it's in the product by default. And yeah, it's there, no matter if you use it or not. That means that we have a few extra components built into SQL Server 2014 that has not been there before. That's the one that marked in green and blue on the slide behind me. Start by the blue ones, that's the memory optimized tables and the indexes. They're located down here. And if you pay attention, we have a blue arrow here, the query interop. That means that we, from our regular T-SQL stack, from our disk-based tables, where we usually write our SQL code, can actually interact with our memory optimized tables and indexes. It's a one-way street, please note that. The arrow only goes one way. You cannot come from the natively compiled store procedures into your disk-based objects. That can only reference the memory-optimized objects. If we start by the top of the slide, we have the client application. Whether or not the client applications connect to memory-optimized tables or disk-based tables is completely transparent to the application. It's the same driver, it's the same everything from an application layer perspective. So in that way, it's transparent and you don't even need to do anything except on the SQL server. You have, of course, to move your tables and stuff like that to memory. But from the application, you can build this completely transparent. So, memory optimized tables, contrary to the word or the name, is actually fully ASIC compliant. Everything by default is stored to disk. It writes the data down to disk, and it writes everything to transaction log as well. It shares the transactions log with the rest of the product. So as I told you, it works seamlessly with current SQL Server objects, and you can mix disk-based and memory optimized tables in your queries as long as you don't use natively compiled store procedures. Same thing, you can span memory and disk-based tables, and it works with high availability. As I said, as long as you're not working with natively compiled store procedures. It's still ACID, and it's still supported by high availability, but natively compiled stored procedures can only work on memory objects. So we're here to watch some code, so let's do that. If we are to create a normal database, we will probably not collate it Latin 1, John 100, bin 2. But if we are doing memory optimized tables, that's what we have to do. So let's go ahead and create our database. This collation is the only one supported, so that's what it has to do. We will then go ahead and we will add a file group. Memory optimized tables used file groups as the storage engine, so every database that's supposed to hold memory optimized tables has to have a file group, or file group storage. So, and we'll tell it where to put that data. This is not a production system, so it's on my C drive. So that's it. Now I have a database that's ready to hold memory optimized tables. That's actually everything that we have to do in order to get started with the product. The same thing, create table. Well, nothing new about that. There are a few things that are new to the syntax. With memory optimization on, and the durability. With memory optimization on just tells that this table should be created in memory. Durability is how we store the data. If it's schema and data, which is the default, that means that the data is stored to disk as well as the schema. If you set schema only, then only the table schema will be stored to disk and data will live only in memory. It means if your SQL server crashes or you shut it down or whatever you're to do with it, you lose your data. But default is schema and data, and that ASIC compliant. The indexes, which are rather important within memory optimization, optimized tables, can be built in two ways, either inline on the row, or as we normally do it afterwards. We have a new index, which is the hash index. The hash index composed of a number of buckets. You specify how many. In this case, we have 1024. The number of buckets should be the number of unique values for your primary key or whatever column you're hashing on. Each value that hashes to the same value goes into the same bucket. And that means if you have too few buckets, you will have multiple values within the same bucket, and that will cost you performance. But besides that, the T-SQL stack is more or less the same. Create table, it's the same data types, same syntax. So, sorry? Yeah, didn't use the database, but I'm not going to use the table in the further demo, so it's okay that request. But we can go ahead and create it and it will work. Yeah. So moving along. As I mentioned, the indexes are pretty important, more important than usual, because it's the indexes that bind the data together. The indexes have the pointer to the next row of the data, and also in the hash indexes, do yourself the favor of getting the bucket count right, otherwise you will be suffering performance hits really, really badly. So do study a bit about the hash index reads up, and it's pretty well documented by now, so do yourself the favor and get to know it. Besides having a hash index, there's also a new type of versioning in memory optimized tables. We don't use locks and latches. We use row versioning instead. So every row has a begin timestamp and an end timestamp, where if the row is still alive, the end timestamp will usually be infinite. So whenever a transaction comes in, starts reading the table, it will see all the rows that has a begin timestamp that's earlier than the start time of the transaction, and an end timestamp that is after or infinite. So if I start a transaction now, and then I insert the row, that transaction will not be able to see the row that's been inserted, because the begin timestamp of the row is after the start time of my transaction. If I go ahead and update a row, an update is a delete and an insert. We don't really update the data. Then we specify the in timestamp of the old row, deleting that, so to speak, and we insert a new one. A transaction that comes in that has a begin, well, a transaction start after the update will not see the old row because it has a timestamp that's after the end timestamp. It will see the new row because that has a begin timestamp that's earlier than that. So that way we are not locking our data. We can insert, we can update, we can read, we can do everything at the same time. And that's also what kind of gives us a performance boost. But this is version 1 of the product. And with everything that has 1.0 and the version number, a lot of things is not supported and a lot of things still doesn't work. So this is just the main ones. You can read them for yourself. The most cumbersome about working with memory optimized tables is the lack of the alter statement. You can't alter any objects. You have to drop and recreate them. And that means if you have to alter an index, you have to drop and recreate the table. So bear that in mind and get it right the first time, or have somewhere where you can do your data off. Also, the very last one, all data has to fit in memory. If you run out of memory, it's the same thing as you run out of disk space. It's just gone. There's no spill to disk. That doesn't happen. But all of this is also, we got the memory optimization advisor that will help us, that will guide us along on how to, what we should take into consideration whenever we start converting our stuff. So we look at how Adventure Works, for instance, is built. Let's go here, go. Any given table. None of them are actually able to convert to memory optimization. But if you have this menu point called Memory Optimization Advisor in SQL Server 2014 Management Studio, that means that the table is disk space. If you can't find that menu point, you are most likely already on a memory optimized table, because then it's not there. But if we start that, we'll just get a small list here, which is checking the table. And as you can see, this one is actually not capable of, well, we need to work on it before we can convert that to memory optimized tables. And that's all the foreign key and constraints and different types of indexes that's not supported. So you can use this to get a rough overview of what work is ahead of you before you start converting your tables and your stuff to memory. And then you can get an HTML report of it, and you'll know what you'll have to work on before you can actually move your data. So, but if we were to just go ahead and create one small table here, whatever. So now we should have a table that is actually able to be moved on one. But at least the wizard is just an next finish. This is still generic. This comes every time. It doesn't mean that there's something wrong with your table. And you can specify if you need to copy the data and stuff like that. Which column should be the primary key. The table has to have a primary key, and the bucket count for your data. And that's it, migrate. Then the wizard will take you to the rest of the steps, and it will generate the new table, move your data, and all of that. This is a way that you can get a pretty cute, quick overview of what lays ahead of you. I won't advise you to actually use the wizard to do the work for you, but you can get an overview of what is not supported within your tables before you start on a project of migration. If you want to know which tables, stored procedures like that are best candidates for migration, the good thing about in-memory tables is that it's table-based, it's not database-based. You can just move one table or a bunch of tables. You don't have to move all your tables or all your stored procedures. So you can do it stepwise. You can start with the ones that are the easiest, the ones that has the biggest impact on the performance of your database, and go from there. In the yeah.
You mentioned that you're not allowed to have 4 key constraints from an in-memory table. Are you allowed to have 4 key constraints to an in-memory table?
On your disk-based tables, yes, you can do that. So if you use the management data warehouse, you'll have a few new reports, which is your transaction performance analysis overview. And that will go in and that will show you which tables and stored procedures are the best candidates for being migrated to memory optimized tables. And natively compiled stored procedures. I don't have much going along on my virtual machine here, so there's no data to show. But that will give you an overview of what is where you should start. What are the best candidates? So the memory optimized tables are just part of the in-memory tables product, and that's not really where the biggest performance gains are found. The other part are the natively compiled stored procedures, which are stored procedures as we know them, but they are compiled to machine code, and they are run as machine code. Whenever you compile a stored procedure, you can actually find it as a DLL in your file system afterwards, and therefore it's linked to memory. That means it's highly optimized, and they perform extremely well. But as that means Microsoft had to rewrite the entire T-SQL stack to be machine code compiled, it also means that a lot of stuff is not there yet. This is one of the focus areas of SQL Server going ahead with the new versions, in the coming versions. And a lot of this is going to change in the future, I'm pretty sure about that. So many of the considerations or constraints that I'm showing you here will go away in the next after that version of SQL Server. But for now, if it worked in SQL Server 2000, it will probably also work in natively compiled stored procedures. But if it was added to the product after SQL Server 2000, chances are that it will not work. At least that's the rule of thumb that I came up with. So, no outer joins, that's a major one. And yeah, we don't have subqueries or CTs and stuff like that. So I'll just show you how they actually look like, these small guys. Again, it's basically SQL as we know it. Well, a few add-ons with native compilation. That's what tells the engine to do a native compile stored procedure. They have to be schema bound. You will have to specify the execution context. You have to specify transaction level and the language. And that's all because whenever you compile this, it gets optimized. The optimization happens at compile time, not at runtime. That also means that if your data changes drastically, you might have to recompile your stored procedures, your natively compiled stored procedures, to get a new execution plan that fits the data. because the execution plan is bound to the stored procedure on compile time and not at runtime, and that is for performance issues. Begin atomic. Atomic means that if it's called within a transaction, it will join that transaction. If no transaction is present, it creates a new one. Besides that, it's SQL as we know it, select statements, but with the constraints I just showed you. Means no outer joins and yeah, no delete with a from clause and update with a from clause, stuff like that. So why on earth would we want to start working with these guys? I mean, nothing really works, right? Nothing is supported, and yeah, you'll have to go back to writing SQL as we did 15 years ago. Well, there's one good reason for it. That's speed and optimization. Microsoft promised existing apps 10 times performance gain, new apps written specifically for this product 50 times performance gain. They are in memory for OLTP workloads. It's not entirely true. I have used them for other purposes as well with good results, but that's what the product is designed for. So jumping back a bit, because when we started this, we said, yeah, well, 10 times, 50 times. Let's see what it actually gives us. Is this really realistic? That sounds like a lot. I'm using the OS stress tool, which is part of the RSS component. It's a tool that queries a SQL server. You specify a database, you specify the command that it's to run. In this case, it calls a store procedure with a few parameters, use memory 1, an order count of 10,000, and then the trick one here, which is called N100. That means how many simultaneously executions of the store procedure should happen. So in this case, we call this store procedure 100 times, and the store procedure inserts 10,000 rows. That means we're adding 1,000,000 rows to a table. So we are moving data from one table to another table. That's basically it. So running that, it cleans out its temporary directory and then starts going. I did the same thing. Was specified use nmem equals 0. That means it runs a disk-based normal store procedure doing this. That took 35 minutes. We won't be doing that today. This guy will be finishing somewhat faster. It takes a bit more than 2 minutes to run. So that's already a performance gain of about 15 times. And that was what made us starting to work with this product or this part of the SQL Server. That was a 15 times performance increase in moving data, because what you'll see in a few minutes when I'll start showing you how we actually did this. The application that or the part of the application that we converted was moving a lot of data. It's an ETL system, and what we tried working on was the part that would do the actual data movements. So as I said, this should be finished in a few seconds. It takes about 2 minutes. You can always see data movement when you're working with memory optimized tables on your CPU load. If your CPU load is running at a roughly 100%, then that means that you don't have any bottlenecks in your system besides the CPU. A native compile store procedure and memory optimized table that is being really inserted data into should cause your SQL Server to run at 100% CPU. So that's also something you should take into account, so you're not blocking everything else that goes onto the system and draining it for resources. But as you can see now, the CPU load is falling. That means that we're almost at the end of the data inside. And the good thing is, well, we didn't do that, but you can actually query the data at the same time. You can query the table without any logs, without anything while this data movement goes on. The only constraint will be the CPU that's being pretty badly beaten up here. So let's see. It looks like it's almost there. we'll leave that running in the background, but yeah, as I said, it takes about 2 minutes. So we got a 15% data increase, and that was what we wanted to get in the application there was. So let's see, 2 minutes and 33 seconds. So a word about what we were actually trying to achieve. We were going to build, well, the application is called Effector, so Effector on memory. Effector is a data warehouse building tool. It's web-based, and basically all the business logic goes on within the database. The portal is used to specify metadata, and based on that metadata, the data warehouse is built, populated, data is pushed through to a data mart, and all up cubes and stuff like that is built on top of them. Contains master data management and security handling for the data warehouse. What we were going to be working on was the ETL subsystem down here, moving actual data through the system. We wanted to do that 15 times faster than we could on disk-based. So, suitable scenarios for V1 SQL Server 2014 memory optimized tables was what was our starting point, published by Microsoft. So the business logic, yeah, primarily in the database, so suitable for that one. We were concentrating on a subset of the tables and stored procedures. We were not going to be putting the whole thing into memory. We were just doing the ETL subsystem. Client-server communication on the part of the application that we were going to convert is really infrequent. It consists of the application starting a SQL agent job that actually pulls off a bunch of stored procedures, so home safe on that one as well. Then came the tricky part, T-SQL surface area. Microsoft recommends basic. That was not entirely what we have. We actually had a pretty complex SQL, with a lot of dynamic SQL, merge statements, left joins, and stuff like that going on that I'll show you in a few minutes. Yeah, data size depends on the size of the data warehouse and how much memory you have on your system. We could fit a system into the memory that we had, so yeah, that was good to go as well. So making a small gap analysis of what the product was set to do and what we needed. We had a lot of dynamic SQL, heavily reliant on foreign keys, primary keys as well. Primary keys are supported. Identity is not. You can use identity with either a sequence or unique identifier. If you're using just the tables, if you're using natively compiled stored procedures, you can't do that because a sequence is a disk-based object, and natively compiled stored procedures can't reference disk-based objects. They can only reference memory-based objects. So that's why there's a small inclusion mark on that one. Inner joins, yeah, no problem in that one. Outer joins won't work. And we used merge statements to move the actual data. You can't use a memory optimized tables as the destination of a merge, not even if it's, well, neither in native compiled stored procedures or regular stored procedures. That's not supported. Moving large amounts of data, we just saw that. We moved 1 million rows in 2.5 minutes. So yes, that's definitely supported. So let's try and get this rocket flying and get this application converted. So let's try and see what we actually ended up doing. So handling the dynamic SQL issue, that was pretty straightforward. At the moment, well, things we started out with was that from the application, that the one building the data warehouse would fill in all the metadata, and from that, a dynamic SQL statement will generate the actual merge statement. I mean, we could change that. We could just persist the actual data movements as each in its own stored procedure, and that would not be that big a challenge for the application, and not be specifically hard to handle. So we could easily shortcut the dynamic SQL and just have the persisted natively compiled stored procedures. The next problem was that all our code was bound or built as merge statements, which would not be supported, and we'll have to come up with a different solution for that. So you see, this is actually what we had to start with. Basic merge statement, which would use a staging table, and from there on, it would left join a bunch of dimensional tables to get the dimensional values for each of those fact rows. And then merge targets and update when matched, and insert when not matched. Classic merge statement. Nothing much going on there. But still, this is not supported with when we optimize tables and native compiled stored procedures. So we had to do something else. And as we, hadn't written the entire specification, so we started out thinking, well, let's just do an insert. We'll insert all the data and start out just by specifying -1 as all our dimensional keys. And then we'll afterwards do an update statement with an integer and home save. We're using just integers here until we found out that an update with a from statement is not supported neither. So back to basic, back to square one. So going around trying to figure out what to do, how to go around this, I came up with an idea of doing a while loop, actually. So this is the stored procedure that we ended up building, and I now go through it. It's not entirely what you would usually do when you're going to move a lot of data. So when everybody else goes set base, go batch mode, move data in large chunks, that's the way forward. That's how we're going to get speed. We actually did the opposite. We went row-based. We're going to move data row by row, and doing that for whatever 1 million, 10 million, 100 million, how many rows there would be in the system. So to get rid of or get around all the shortcomings of the product, we needed, first and foremost, we needed to be able to do an identity column. We needed to have a unique key in the system that would always be a sequence of values without any gaps. So we start out by finding querying what is the present max row in the table. In this case, this is what loads our employee dimension. Then we will declare the columns that's in our table, and we'll start just doing the while loop. We'll then fill the variables with the value of the current row. So setting each of these values to the value of the row that we're going to treat at the moment. One more variable to tell us, does this line exist within the destination table or not? And then we just query the destination table and asking, do you have a value that has this business key? If you do, then we'll need a few more information about it. We'll need to know what the parent key is. And yeah, well, in this case, that's all we needed. So if this one hits and has an entry in the table, it will get a value of 1. Otherwise, it'll be the default value of 0. So if the line exists, or it doesn't exist, sorry, if the line exists is equal, or is 0, then that means that we know that we don't have a match for this line in the destination table, and we need to insert it. If it's 1, then the value will actually be in the table, and we'll need to update the table with the new value or whatever. We don't really check for if the value has changed or not. It's faster to just do an update than to actually do the checking for changed value. Similar example, it's basically the same thing that goes on. This is just the fact table, which means that there's a lot of more columns, but it's the same thing and not so much checking about it. But still, declaring all the values within the table, and we start the loop, select the values for each of the columns from the current row, and we do a dimensional lookup here, where we're going and selecting if the employee ID from the employee dimension that corresponds to the business key. In here you can actually do a foreign key behavior, because if this doesn't yield a lookup value, you can just throw out an error here. So doing this, you will have foreign key support. Same thing for all the keys that we look up. In this case, we don't really matter if a key is found or not. If it's not found, we'll just give it the value of -1, but if it's found, we'll need to know what it is. Still looking up, seeing if the row exists within the table or not, based on the sales order number and the sales order line number, which is unique in this system. So if line exists is equal or is 0, we'll just insert the values specifying the foreign key values here, but then it's null and then a -1 if we don't have a lookup in that. And otherwise, doing an update if the value is already in the table. So doing this, we got merge statement behavior. We can insert and we can update the data depending on if it's in the table already. We have a left join, so to speak. We do that at the top. If here we go, we select the key from another table, and if it's not there, then well, it's an outer join behavior, because if it's not, the value just becomes nothing, becomes null, and we can treat it as that. So we actually have the kind of a left join here, right? And then we just increment the loop, and we go by the next row and the next row and the next row like that. I have a small integration service package here that I will actually show it for you when it's running. So let's try and give it a fire it off. So let's see if we can make that fit the screen. Can you still see it on the back? Good. So what this here does is that it starts out by deleting all the tables of the dimensions. We don't have truncate and memory optimized tables, you only have delete. It then calls a store procedure similar to this one for each of the dimensions. And it calls the fact down here. And just to see that I'm not telling you stories, reload 1 million rows. And after that, we call the store procedure that we just went through. Oops, sorry, this one. And that loops for each of these million rows. Yeah, and then it pushes all the data out to data mod. It's already done. As you can see, it took 55 seconds to run. And that means we have actually merged a million rows in 55 seconds and done the left joins and stuff like that. We have done what business-wise is the same thing as this merge statement does. The exact same behavior and the exact same thing that we get at end of the day. Just doing it row by row in a loop. And any ideas how long the merge statement will take to run, on how much? Well, you'll be a bit surprised actually. If you look at the statistics here, merging, well, not 1 million, but 10 million rows. And the loop that we just showed you, it took roughly 5 minutes, 312 seconds. Doing the same thing with a disk-based merge on the same hardware, we're talking my laptop here. It took around 40 minutes. So we actually obtained an 8-time performance increase by writing loops and being row by row instead of using a merge statement. So in that sense, well, we didn't completely get to the 15 times performance increase, but we did get an 8 times, which is also pretty neat. Yes?
I have a question about the merge statement. How efficient is that?
Sorry?
How efficient is the merge statement? Could you make it faster in disk-based tables if you wrote something clever yourself?
I'll just repeat the question for the microphone on this. It's just if we would be able to optimize the merge statement by doing something differently, right?
Yeah, while keeping disk-based.
Yeah, and keeping it disk-based. We would probably be able to, but I mean, a merge statement is in itself a pretty efficient way of moving large chunks of data. So I like this in there because a lot of effort has already been going into the product to make it as fast as possible, and the merge statement and the table layouts, indexes and stuff like that were already optimized as much as possible, or to get the data movement to going as fast as possible. And indexes were being dropped and like that before we actually start the actual data movement. So you might be able to get it to 35 minutes or something like that, but I'm pretty sure we won't be able to get the merge statement to 5 minutes.
How fast is the store procedure you just wrote on disk?
The while loop on disk? I haven't even tried it. I'm pretty sure that I will be in London before that will finish, actually. Yes?
The table you had focused on, the outer join tables, were they also in-memory tables?
Yes. This is a natively compiled store procedure. That means that all objects referred has to be in memory tables or memory objects. So yes, every table here is memory optimized.
Are they schema only, or?
In this case, the staging tables are schema only because we don't really care if we lose that data. We can always draw it back in from the source system. But the tables that write data to, the actual data warehouse tables, are schema and data. So that means data does get persisted to disk. Any further question? Let's just, yeah.
So how much memory do you need for that kind of solution?
That depends on the amount of data. The recommendation is that you should have twice the amount of memory as you have data, due to the row versioning. So you might end up have multiple copies of the same rows due to the versioning. And yeah, that's why the recommendation is twice as much memory as data. I have 32 gigs in my lab, and that's enough to move 10 million rows. But much more than that, it will start to be a bit on the edge. So what to do if you have more data than you have memory? So I guess that turned out to be an excellent question, which is a question that's on the next slide. Well, it's not on the next slide, but it's on the next, the next demo. If you don't really have as much memory as you have data, you can go ahead and do what is usually, well, the concept that I wrapped it off is the partitioning view. So we will have a table which is a normal disk-based table that has a constraint. So this is where the sales order IDs of this table has to be between 50,000 and, well, 99,999. So doing that, SQL Server would know that that's all that can be in that table. And that is disk-based. So we'll then create a memory-based table. And on memory-optimized tables, we can't create constraints. So in that case, we will not be able to do a constraint on that. So I will actually be able to hold all kinds of data, but we will only use it to keep the first 50,000 rows. We'll then put a view on top of those two tables. Just a straight union all. We will not be able to write data to this view because it's not partition view compliant. One of the tables doesn't have a constraint. So if we get a row in that's between 50,000 and 99,999, SQL Server will not know where to put that row. Should it go into the in-memory table? Should it go to disk-based tables? It can go to each of those two tables. So you'll need to build that into your data, the store procedure that loads the data of whatever you use to load your data, which data should go where. But you can use it to query the data. And SQL Server will know that if you query data that is in the lower range, that means with a sales order ID less than 50,000, it cannot be in your disk-based table because that has a constraint that says the data here is from 50,000 and upwards. So we know that in that case it should go down and should start looking for that data in your memory optimized table, which is fast. And only for those rows that has a sales order ID of 50,000 or above, it would go out and look into the disk-based table. So you can use this to create kind of a hot and cold data zone where you keep the data that's that's queried often, but in your memory optimized tables, and the least frequent queried data on disk. In that case, you'll be able to fit much more data in than you actually have memory. So that's one way to go around that. So basically, when working with memory optimized tables, it's a matter of imagination and what you can think of, what you can dream of. Try stuff that you will usually never ever do, that you will know by heart and mind that will definitely be a bad road to go on. it might actually work on this stuff because it's not SQL when it's executed, and bear in mind it's executed as machine code, and strange things happen whenever you execute it. So in that case, go around trying out stuff that will seem a bit off, because it might be the road that is actually has the gold part at the end. So yeah, natively compiled stored procedures are not T-SQL. Well, they're written as T-SQL, but they're not executed as T-SQL. I put in a few references here at the end, and as I said, you're very welcome to contact me afterwards. Twitter handle and stuff was on the first slide. The code examples that we have been using today, let me just put that at the end. But the code examples are all on my blog, at the very least point on this slide. So you can get them there where concepts are explained once more, and there are a few comments there that will more or less walk you through trying to do this by yourself at home. Otherwise, yeah, feel free to contact me and ask a question. Be happy to help out. So I hope you will enjoy the rest of this conference and what PARS otherwise has to offer you. We are a bit early here, so we have time for some questions if you have. Please feel free to fire them off. Otherwise, I'll be here for 10-15 minutes more than I'll need to go to the airport. So, thank you for your time.